We're surrounded by fabric every single day. But have you ever stopped to think about what's going on inside the threads? Well, it turns out there's a hidden code, a whole language of geometry that dictates literally everything about your clothes. Today, we're going to crack that code. Think about it. Why does a silk scarf feel so different from, say, a rugged canvas bag? It seems like a simple question, right? But the answer isn't magic. It's actually all about math and engineering, and it starts with the absolute basics of how fabric is made. So let's get right into those fundamental building blocks. To understand the code, you've got to learn the alphabet first. And for fabric, that alphabet is warp, weft, and weave. Okay, now this might look a little complicated, but at its heart, a woven fabric is incredibly simple. What you're seeing here is just two sets of threads interlacing with each other at right angles. That's it. You've got one set running up and down and another set running side to side. So those vertical threads, the ones running up and down, they have a special name. They're called the warp. You can think of them as the backbone of the fabric, running along its entire length. In the textile world, they're also known as ends. And what about the horizontal threads, the ones that weave across the warp? Well, those are called the weft. They go from one side to the other, and you might also hear them called picks. So it's warp and weft, or ends and picks, all woven together. And this super simple structure is just genius. The way the threads interlace so tightly gives the fabric its strength. But because those threads can still shift and bend a little, the fabric stays flexible. It's this perfect balance of properties, something we figured out thousands of years ago. So if warp and weft are the basic ingredients, how do engineers control the final result? This is where the recipe comes in. The specific settings and parameters they tweak to design the exact fabric they're looking for. Very first ingredient in our fabric recipe is thread count. You've probably heard this term when you're shopping for bed sheets, right? A higher count usually means a softer, smoother feel. But for something like a tough canvas bag, you'd actually want a much lower count of thicker, stronger threads. It's all about density. All right, now for a really crucial concept, but one you might not have heard of: crimp. Crimp is basically just the waviness of the yarn. It's that up and down path a thread takes as it weaves over and under all the other threads. And this picture shows it perfectly. See on the left, that natural, wavy path of the yarn in the fabric? That's the crimp. Now, what's cool is that it acts kind of like a tiny spring. When you pull on the fabric, like you see on the right, that wave straightens out. This is what gives woven fabrics that little bit of stretch and give. So here's the kicker. By controlling just the amount of crimp, an engineer can control all of these things. We're talking softness, thickness, durability, how well it covers something. It even affects what's called the hand of the fabric, which is just a fancy term for how it feels when you touch it. It all goes back to that tiny wave in the yarn. Okay, so we know we can control these properties, but how do we predict what they'll be ahead of time? How do we make a blueprint? Well, this is where science had a major breakthrough, by turning fabric into a solvable geometry problem. So we need to talk about the pioneer of this whole field, a guy named F.T. Pierce. Back in 1937, he was the first person to develop a mathematical model that could look at the geometry of a weave and actually predict how the final cloth would act. This was absolutely revolutionary stuff. Now, to make the math even possible, Pierce had to start with a few simplifying assumptions. He basically imagined that the yarns were perfect little circles that were totally flexible, couldn't be squashed, and couldn't stretch. Now, of course, that's not exactly reality, but it was a brilliant starting point for the blueprint. And here it is. This is the blueprint itself, the core of Pierce's model. You can see the circular cross-section of the threads, just like he assumed. This diagram shows the exact geometric path one yarn takes as it weaves over and under another. Every single angle and curve you're looking at can be described with a math equation. And this is what's going on under the hood. Now, don't worry, there's not going to be a quiz, but what these equations do is show the relationship between things like how thick the yarn is, how far apart the threads are, and what the final shape of the fabric will be. And of course, the more factors you try to account for, the more complex the model gets. These equations start to bring in properties like crimp and thickness, which makes the predictions even more on the money. Ultimately, all of this complex math is what turned the ancient art of weaving into a modern, predictable science. It means an engineer can design a fabric with very specific properties on paper, long before a single thread ever hits the loom. Pretty amazing.
So, what happens when you push all this geometry to its absolute physical limit? I mean, what if you try to pack as many threads as you possibly can into a piece of fabric? Well, you get a condition called jamming. Jamming is pretty much exactly what it sounds like. It's the point of maximum density. The best way to think about it is like a parking lot that is so jam-packed full that you couldn't possibly squeeze in one more car. For fabrics, this creates incredible durability. We're talking tough denim or ballistic nylon. Those are designed to be in a near jammed state.
And there are two main types of jamming. In warp jamming, you've packed those vertical threads in so tightly that the horizontal weft yarns have no room left to bend. They're literally forced to become completely straight. And, you guessed it, the exact opposite is true for weft jamming, where the vertical warp yarns are the ones that get straightened out. This is the absolute physical boundary of weaving. Okay, let's zoom back out for a second and bring this all home. Let's connect this science from the simple thread all the way to the t-shirt you might be wearing right now. Everything, and I mean everything, about the clothes you wear is the result of a deliberate choice. The thread count, the amount of crimp, the type of weave, it's all been calculated using these geometric models, all while respecting the physical limits of jamming. The softness, the strength, the way it feels, it is all by design. So what's the big takeaway here? Well, the next time you get dressed, maybe you pull on a favorite sweater or a comfy pair of jeans, just take a second to think about the incredible science that's literally woven into it. You're not just wearing clothes, you're wearing a carefully engineered masterpiece of geometry.